Yeah, thanks to the organizers for inviting me. It's been a really fun conference so far. And keeping on theme, well, at least with most of the talks today, I'll also talk about floquet codes and getting a little bit more abstract again. But I will try to tie it back to reality a little bit. So hopefully it makes sense to people who aren't deep into the topological world. And before I start, I should say thanks to a few people who probably are the reason why I was thinking about this in the first place. So this all kind of came out as a suggestion from MISM to think about what this topological defect network framework, which I assume probably a few people know what I'm talking about there, and I will explain that. But it's some framework for some topological states we've been thinking about in the last few years. And he asked me what this means if you extend it to space-time. So we were doing everything sort of statically in space, and you could sort of obviously add some sort of time direction. And this sort of motivated a question. And then I got to thank Ben for kind of helping me understand how this key example from Hastings and Haah fits into this picture, and then sort of ongoing discussions with Dave, working everything out. Cool. So before going into super generalities, this conference is meant to be about NISQ, I think. It's in the title. And I think, although I'm going to talk about very abstract things, they are rooted in probably a question that's motivating most people in this room, which is, we want to make quantum computers, so how do we do that? And Alex gave a very nice overview of sort of big steps in that. And what do we do with them if we do make them? So we're thinking specifically at the moment about being in this early era where we don't have error correction yet. But although we don't have error correction that's scalable, we're still doing a lot of things towards that. Like we need to go and characterize how the devices are working, learn about the noise, think about how we're going to do the error correction, start testing it even though we're not below threshold. And there are really interesting experiments doing this now. On the other hand, when we're in this NISQ era, we want to think about simulating interesting many-body systems, especially ones that will be inherently robust, so we might get some meaningful results out when we simulate them for a short time and then measure some properties. So both of these things, I think, tie nicely into topological order. So essentially, topological order, which I'll show in a slide or two, is the condition that you are an error-correcting code against local errors. So as long as you have sort of some locality, geometric locality, going on in your setup for both the sort of checks you can do, the measurements, and also the sort of noise that happens, I think you will want to use topological codes. So essentially, you want to use some sort of topological phase, and in some sense, simulate it while doing some feedback to correct errors. On the other hand, if we want to think about what sort of systems might be inherently robust in this sort of early era before we have error correction, we want to do some interesting simulations. And there are sort of real experiments already doing this. Super cool. The kind of systems we want to simulate also likely have topological order, which would give you some sort of robustness against some sort of local noise and some sort of existence of a sort of phase that's not super fine-tuned. Okay, so I'm going to sort of go on to some very abstract things about topological orders and how we think about classifying these things. But these questions, I think, a really nice thing is that now we have people over the whole spectrum from like category theory to experiments talking to each other, maybe not directly, there's some people in between. But we really get some motivations, like we come up with some cool code ideas and then say, maybe you want to try and implement it this way, and then maybe someone does it. And then they say, oh, there's these things that come out of experiments. And we kind of abstract those things we don't understand into some conditions we plug into our code search to find new and interesting codes. And that's sort of where this abstract nonsense I'll tell you about in this talk comes from, some motivation of trying to make measuring the stabilizers to do error correction more efficient. And then this sort of motivates this floquet code, which we've seen a few times today from Hastings and Haah, which then motivates us to try and understand some new set of sort of topological phases where we don't just have statics, but also measurement dynamics going on. Okay, so let's get into that. I'm going to start with a bit of background. I don't want to assume everyone here is sort of super topological, and give you sort of a definition and also the canonical example, the toric code, and then say a bit about why we, or how we generally abstract away the lattice to reason about sort of high-level properties of these phases most of the time. Then I'll move on to tell you about how measurements are related to dynamics in these phases. So the first bit will be all sort of static background. Second bit will be some things that are very, very obvious to you if you do quantum error correction, topological quantum error correction, but maybe are things people who work on phases of matter don't think about as much. And then finally, I'll tie it together by introducing this sort of extension of this topological defect network formalism to spacetime and try to explain why that describes these floquet codes and how you'll get sort of new examples from that. Good, so let's start at the beginning. I'm going to give an abstract definition, so if you don't like that, just check your phone for like 1 minute, and then we'll do an example. So this is just making this statement I said a minute ago more precise. So this topological order condition is phrased in terms of what I like to think of as a projector onto some degenerate ground space of a gapped and local Hamiltonian. Local on some geometric space, usually we consider like a lattice in Euclidean space, so you could think of like the square lattice. And you have some finite dimensional degrees of freedom, that's what I'm going to think about, qubits, living on, say, vertices of this square lattice. And then we have this Hamiltonian, which is given by a sum of local interactions respecting the geometric locality. And we want this to have a gap to provide some sort of robustness or stability of the phase of matter of this Hamiltonian to perturbations. So if we consider this projector, it's not guaranteed to already be a topological phase. It needs to satisfy this extra condition, which I'm calling topological quantum order here, following Hastings and collaborators. And this condition reads, so let me just unpack this a bit. If you consider an arbitrary local operator, and we're kind of considering an infinite system here, so anything with a sort of bounded radius that's not growing with as we increase the system size off to infinity. And when we sandwich that local operator into this ground space projector, so that's basically saying, well, take the ground space, apply the operator, maybe it creates some excitations, but we project it back to the ground space, throw those away, and see what it does. It just acts like a constant. This constant can depend on the local operator, that's fine. But essentially what it does is only act like the identity on the ground space. So if there's some kind of encoded information in some of these degenerate states, it's not going to do anything to them. That's the idea. And this is not quite the Mill-Laflamme error correction condition, but it's closely related, and I think it's worth just saying a thought about that. The idea is that we're going to have some sort of practical scheme to actually implement this projector, or to measure into the projector and the sort of orthogonal space. And so if some local error happens, we'll do this measurement. If we go back into the ground space, we're happy. It just did the identity gate. If we go to some orthogonal excited state, we're going to use this sort of syndrome that we got from measuring, actually implementing this sort of measurement, to come up with some correction operator. And the key thing is this will also be a local operator. So then when we multiply this correction, which takes us back to the ground space, with the original local operator, in this kind of infinite limit, the product of two local things is again local. So overall, this condition will tell you that you are an error correcting code against local operators. Good. Now for less abstract example, if there's one thing I've learned, I guess, in my 10 years of doing this, you've always got to have a slide on the toric code. So here's a few slides actually, and I'm drawing it in this way that maybe some of you are familiar with, where I've rotated the lattice and put the qubits on vertices. I'm going to abstract the lattice away in a minute, so if you don't like this lattice, don't worry about it. We're going to get rid of it soon, but here's a concrete description of some small toric code. I have these little dots, which are meant to represent 1 qubit per vertex of this lattice with periodic boundary conditions. I bicolor the faces of this lattice, and I put X stabilizer checks onto all of the gray faces and Z stabilizer checks onto all of the white faces. You can check they commute with each other. And now the eigenvalues of these, the excited states of these stabilizers, or the syndromes, will define some anionic excitations. They're sort of called anionic because they're non-trivial superselection sectors, and you cannot make them locally. You can see this from some constraints that if you take the product of all x's on this periodic boundary conditions, you get the identity. So these have to come in pairs. So you can't do anything sort of locally to create a single one. A pair of them you can create locally. And so here's just some explicit string operators. So you can kind of apply a bunch of z's, and that will create what I'm calling e's. The labeling of E and M is arbitrary, as we saw in the last talk. And similarly, a string of x's will create a pair of m's. And you can sort of move them around the lattice. They can walk freely by applying these string operators. Good. Hopefully that's pretty familiar. And yeah, if you kind of wrap these these paths around the lattice so they kind of connect in a non-trivial, topologically non-trivial way, you get logical operators. You can check the commutation relations there. They give you a -1. And you get 2 pairs of them, one where x is sort of along the vertical and z the horizontal, and vice versa. And that gives you a ground space degeneracy of four states here. So you can work this all out from the lattice. Okay. And before I go to the high-level picture, I want to show a few more features. So this was sort of just anyons and no open boundaries. But it was quickly worked out after the model was proposed by Kavli and Bravi how to put sort of open boundary conditions, which is sort of important if we don't want to have some long-range interactions in our sort of flat, chip. And this works by sort of just modifying. First, you can think of throwing away all the stabilizers at the boundary and then putting some back in. You can't put all of them back in because they'll no longer commute if you have these kind of truncated stabilizer terms. So you have to make a choice. But it turns out if you just sort of pick, say, all of one type and put it back in along the boundary, everything commutes and you've fully gapped it out. There's no local degeneracy left. So I have these two new types of stabilizers, the boundary X and the boundary Z. And you'll notice now that I can actually deposit here, say, an E charge into the boundary by applying a string operator that terminates in the boundary. The reason why there's no excitation at the boundary now is because I threw away the type of floquet that would be excited by that string operator. And vice versa for this gray boundary, you can condense an M there. So the sort of high-level information you need to keep there, or that's important to abstract there, is that you can have sort of one boundary type where E is condensed and another boundary type where M is condensed. Condensed is just jargon for you can locally create it. That is sort of important because if we were away from the boundary, the sort of defining property of these things is you can't locally create them. So near these boundaries, the effect of sort of introducing a defect is that you can have different condensations. And we'll see later that the way you actually specify these in this abstract formalism is by what condenses there. Okay, and again, yeah, you can find some logical operators. So here you'll get a ground space degeneracy of 2, and you can compute this sort of property from the lattice. Good. Final property of toric code before I abstract things. Following bump in, we can also insert these sort of twist defects. So we insert some kind of dislocation into the lattice, and you see that this kind of messes up the coloring. So the black coloring kind of discontinuously changes to white as you cross, or the gray coloring changes to white as you cross this twist line, which I've drawn as a dotted line. And this also messes up some stabilizers at the boundary. So I have some new stabilizer terms in this region. Everything away from that region is the original ones. Here I modify this sort of twisted one that crosses the domain wall by just flipping some of the pallies. And then at these boundaries, I have to find some new combination that commutes with everything, and you can do that. The key property of this is that if you sort of go and check the string operators, it will indeed map an E to an M as you cross there, as you can kind of expect from the coloring. So although E can never be turned into an M locally, if you're near this defect, if you kind of go across this defect, you can turn an E into an M. And a sort of technical point is to actually compare that in a gauge invariant way. You need to terminate this so you can actually bring the M back around and put it next to the E. Because if they're sort of living in different regions and you can't make them near each other, there's a relabeling freedom. Okay. And another way of saying this, that you can turn an E into an M, is that if you have a pair of an M and an E together, you can condense them, which means, yeah, locally you can create this thing. This sort of composite particle I'm calling psi, I think it was F in the previous talk, because it has the self-statistics of a fermion. Good. So by introducing these boundaries and twist defects, we get some kind of non-abelian objects where things can condense now. And if you want to understand more about sort of all these different things you can do with toric code, I recommend you ask Bernie. He has a nice paper on this explaining how these sort of defects between the two different types of boundaries are the same as these twist defects. Okay, so I think that's kind of everything there is to know about toric code, more or less, at least statically. And usually, if we want to kind of do some high-level reasoning, we don't actually draw a lattice every time. We think about abstracting away these details and just keeping the key topological features. And when I keep saying topological, essentially what I mean here, what we usually mean is basically all the operators and all the objects going into this description are deformable. So the property doesn't, the key properties defining them, such as what condenses there, it doesn't change if I just deform it a bit. Okay. So we kind of throw away the lattice, and we have this formalism, this sort of algebraic formalism called topological quantum field theory. I'm not going to go into any definitions or something, don't worry. You can just think of it as some way of, some black box that assigns different data to spatial regions and tells us, given this sort of topological phase, say the toric code here, what will the anion types be? What will the ground space degeneracy be on the torus, for example? Once you know the anion types, you know some string operators should come along with them. And furthermore, you can kind of go and solve properties beyond just these ground space and anion properties, like what defects can possibly appear there, and what kind of boundaries. And here I'll also just mention some terminology. So this defect here, which everything passes through without being condensed at, this dotted line, is like an invertible sort of defect, whereas these defects at the boundary where things condense are non-invertible. Okay. So often if you want to kind of come up with some abstract topological scheme to do some things, you'll start with this sort of reasoning. And if you want to classify things at like a high level, not worrying about some details where two things might be sort of the same under an equivalence relation, but you've just added a qubit here, say, you want to work with this kind of formalism. And then obviously when you want to go and do something, you need some techniques, some machinery to like turn this into an actual list of measurements you do. And then, in reality, you then have to turn that into like what you actually do in an experiment, but that's totally beyond me. So let me stick to this sort of high level stuff. Good. So the classification we're interested in of these topological orders to kind of wash out the local details that don't change the qualitative properties. I'm going to just sort of describe succinctly here. It's not quite correct, but morally correct. Is that you want to allow local unitary circuits on this projector onto the code space. The reason you do local unitary circuits is because it preserves locality of the errors. So if the original thing was this sort of topological or error correcting condition, you conjugate by local unitary, it keeps the local operators local, so the new thing will still be topologically ordered. You also want to do some stabilization, like allow yourself to throw in some trivial qubits. Like say you have just some extra qubit in 0 state and you just put it into the lattice, this shouldn't change the phase you're in. So here what I mean by trivial state qubits is anything that's in a product state, but we could just sort of fix a product state once and for all and say like adding projectors onto the 0 state of decoupled qubits is an allowed operation. And let me just quickly go through what's known from like the past few decades of trying to study these things. In 1+1 dimensions, I'm going to use this kind of high energy labeling of dimensions because we're going to start introducing spacetime at some point. So in one spatial dimension, everything is trivial if you have this stability condition. And there's a nice proof of this using sort of tensor network formalism. We don't have time for that. In 2+1 dimensions, this story about anyons is believed to be everything. And I think you can actually, recently there's progress by Isaac Kim and collaborators on sort of showing this based on a few assumptions. Still, I think an open question to show this with like sort of really minimal assumptions, but it's widely believed that this sort of anyon theory, plus another detail that I'm not going to get into in this talk because it's not going to be super important, that when you make this sort of edge, generically, you actually can't gap it out as we did in toric code. And then the detailed information of the edge can actually give you a bit more information than just the anyon theory, although there's some conditions that they have to satisfy together. But there's quite a good handle on these things to the point where it's kind of become a math problem, and it's a hard problem, but nonetheless. Good. So that's sort of the story everyone believes in 2+1D. And what about 3+1D? This has been quite interesting for the last maybe 5 years or beyond. And interestingly also came out of some ideas from error correction. So let me start with the simple case. If you have this kind of topological order we call liquid type, which just means after maybe some initial coarse graining to wash out some fine-tuned effects, the ground space dimension, for example, of these things doesn't change if I change the length of the periodic boundary conditions. It only depends on topology, like you would expect from a topological thing. And there's a nice argument from Wen and collaborators that these things, these liquid topological orders, are some kind of generalized gauge theory. I'm not going to go into the details of exactly what kind of generalized gauge theory you need there. You need to add fermions, these things called twists. Different kind of twist to the one I introduced before. But maybe just take away that we have kind of good tools to reason about them, although there are still some things about those we don't understand super well. We have a reasonably good handle. But you also get this other type of funny topological orders that came from famous examples by Shimon and then later Jung-Won Ha when he was thinking about sort of an error correction problem. And these initially looked very not topological. They have some property where as you change the size of the lattice with periodic boundary conditions, the ground space degeneracy can increase exponentially with a linear system size and also can jump arbitrarily. So it can jump from exponential of L down to like a constant number and then back up. It can do really crazy things. There's a bunch of nice ways to understand these. And I think maybe, let's say probably in my opinion, the most general way of understanding these is actually back in TQFT world. So it turns out they're not beyond TQFTs. They just require adding some extra structure to these TQFTs. And the structure you need is to take these sort of defects I showed you in toric code. There's some version of those in 3D. And you need to take your big block of TQFT of this sort of liquid type. And then, I have a slide on this actually, okay. You need to take a big block of this sort of liquid type topological order, which is, so let's say, simpler to describe. And then you solve sort of what defects this thing can have, which the topological quantum field theory tells you. And you insert these along some lattice. You have some points where they meet and you need to, so these are like these 2D defects. Then these meet at these like seams. You need to like find some consistency condition on the seam. This is also told to you by topological field theory. And then finally at the points you have some kind of charge that can live there. And you have to decide what that is. But with all this specified, it gives you sort of a semi-lattice model within TQFT that can describe, at this point, we sort of conjecture it describes everything, at least based on finite degrees of freedom. And we have a proof that it can describe all, at least CSS stabilizer codes on a cubic lattice or hypercubic lattice. And I had a little ... before because you can kind of continue this to beyond sort of physical dimensions, 4+1 and so on. And then I think things are kind of similar to the three-dimensional case. There is a simpler class of liquid-like things, and then there are these defect networks you can have. But I'm going to stick to sort of 3D for the rest of the talk, 3+1. Good. That's probably a good place to stop and ask if anyone has any questions they want to ask about the background before I move on to sort of dynamical things. If not, I'll continue. And we want to think about these sort of more general dynamical situations where I don't just have some ground state just sitting there. I have some interesting things going on that change over time. Good. So the most naive thing you would think about is like, what's dynamics? I just exponentiate the Hamiltonian, right? This is actually super boring in all these stabilizer models because they just commute, so everything's just static. But this is a bad place to look. And if you kind of look at this dynamics, it would look like it's all just trivial, dispersionless. But if you kind of do topological error correction, you'll be very familiar with, and topological quantum computation, you'll be very familiar with the idea that the kind of dynamics you want to look at is adiabatically dragging around defects to braid anions, or do lattice surgery and so on. And this, there are sort of two approaches to this. One is you imagine sort of adiabatic dragging, sort of having a trap potential in Hamiltonian and moving it slowly, maintaining the gap. But another thing that the way people actually mostly think about it in error correction is you just do these things instantaneously by measuring. So you do measurements to kind of create defects and move them around at your will. Good. And this kind of ties in nicely to things people have been thinking about more recently from the phase point of view, where there has been a bunch of effort on looking at how adding phases to kind of adding measurements to quantum dynamics can lead to interesting new phases. And I think this is one of the motivations for the floquet code, as Young-Han told us. Okay, so let me just start with like a super simple example, I think, of a kind of space-like defect. So these are maximally different to the things I was showing before, where you have some defect statically sitting there in time, and it sort of has some time extent and some space extent. These defects will be purely space-like. They just happen at one instant of time and then they're done. We do these really routinely when we think about initializing, say, the toric code. So we'll start with, say, all plus states on our qubits and just measure the SZ stabilizers because the SX stabilizers are already satisfied. Another simple example is doing like a single qubit readout on all the qubits. So we take some toric code state and just measure each of the individual qubits in the X basis. There are similar things you can get by swapping X and Z, and those will just swap the roles of E and M. Good. So here's a little picture. We want to kind of abstract this to some topological information. And the initialization ends up just being one of these M condensing boundaries in my convention of labeling at some instant of time. So you start with like there's nothing there, or qubits in a product state count as nothing from this high level point of view. So you have your qubits in a product state, and at some point you measure into the toric code stabilizers, and you have your toric code, which I've drawn in this sort of block. And then it just sits there for some time. And then at the final step, you do a readout. This ends up being like a final projection M condensing boundary. So all of the M's condense out of the toric code. And if you had any E's in there, they'll become some kind of confined thing. So before they would be point-like, but once you have the sort of measurement result, you'll see some lines connecting them. Okay. And an interesting sort of feature that appears here is you can have these like time-like anions, sort of world lines that can go from one boundary to another. So these are kind of like a time version of this space-like anion line string operators that can go from one space boundary to another. Okay, so here's a simple example. And we can start to use these kind of simple things we know exist in toric code to build up, say, floquet code. So what is a floquet code? It's going to be some of these sort of code-like procedures just repeated in time. So floquet just means you have some fundamental time step, and then you have time translation symmetry, so you just repeat that a whole bunch of times. So the simplest example I can think of is just this project onto the ground space of the toric code. So to actually implement that, you would probably want to just measure all the stabilizers of the toric code at every time step. And this is actually basically how you do error correction. And I should note here, I'm not explicitly including information coming from the randomness of measurement results, or say if you had actual errors that would cause anions to appear. So if you're really implementing this, I'm just sort of showing the skeleton, the scaffolding. There would also be a bunch of anion world lines inside here based on sort of the measurement results you got, and if you had errors causing anions to appear and propagate. But I'm just keeping track of the phase in which this all happens. Okay. Let's go into a slightly less trivial example than just the toric code sitting there. We can think of having this kind of EM swap defect. I showed this in space. You have an E that goes across this invertible defect to become an M and vice versa. And you can do a space-like version of this. There are lattice models for this. You could also implement it in this one I showed you by sort of translating the white onto the gray lattice and doing a Haah-Hastings. In this abstract picture, this is just some event that happens at a certain time slice and swaps E to M. And it's invertible and actually has Z2 fusion rules. So if you coarse grain like two of these periods together, this is actually equivalent to the one on the left. So if you don't have this kind of time translation symmetry protecting it, these two are equivalent. And I wanted to just make a small comment that I think that this sort of high-level formalism in some sense should kind of unify these sort of measurement-based versus floquet SETs. I'm not going to claim anything like rigorous, but I think this kind of TQFT with invertible defects should be a high-level description of the evolution of subspaces in this floquet SET story. And I'm basing this off these nice papers by Thorngren and else, where they did a space version of this. They had some Spacelike space group protected SETs, and they came up with this invertible defect network that we actually took and then made non-invertible to do what we wanted to do. And if you extend that into space-time, you essentially get one of these invertible space-time topological defect networks. Okay. But we want to move on to these non-invertible ones. So these kind of things we do in error correction all the time that I showed here are non-invertible because we really have some things condensing or uncondensing being engaged at certain time steps. And that gives you a lot more possibilities to play around with. Good. So let's plug in this simple example to see what floquet codes we get. Well, sorry, I won't call them floquet codes. We won't have any encoded qubits, but we'll have some sort of floquet topological orders, if you like. Okay, so I want you to look at this for a minute. Let me explain what I'm doing here. These blocks are just toric code, and on the left, I'm initializing with the M boundary and having a readout, which is corresponding to the M boundary, and then just repeating that. On the right, I'm initializing with the M boundary and having a readout corresponding to the E boundary. And if you think about it for a minute, I want to take a vote, like who thinks that as a sort of measurement-based topological phase, which I haven't given you a definition for, this would be trivial. So let me get like hands up for who thinks this dynamics would be sort of trivial in some sense. Does anyone think this would be trivial? I'm just like initializing a toric code, then measuring it out. All right, seems like people don't know. If you think about the right one, do you think the answer would be the same? I'm doing something pretty similar. I just switched E and M in some place. And I find it kind of hard to reason about what sort of phase of matter I have in these things, and even if it's sort of stable. So a nice thing you can do with the space-time topological defect network picture is because everything kind of, in this TQFT formalism, time is just like, it's like Euclidean time. It's like another space coordinate. You can freely rotate these things into each other and compare things. So if we just Wick rotate this whole thing, we turn time into a space coordinate. And you notice that along X and Y in this dynamics, nothing's happening. It's just like homogeneous. So say the X coordinate here becomes like, sorry, it's going this way, becomes time. And the time coordinate becomes X. We now have these non-trivial stuff happening along Y. And so I think I've drawn this wrong because I've swapped T and Y here. Yeah. Okay, so we now have what was happening in time now happening just along the Y coordinate, and what was happening along the Y coordinate, nothing is now happening in time. So this is just a static ground space situation. That's kind of the same as this, just rotated. And now we can easily reason about these with things we know. So on the right-hand side, you have these strips of toric code, these thin strips coming from the small time steps where the toric code exists. And on one side, you have an E boundary, on the other side, you have an M boundary. And you can go and check explicitly that you can just disentangle this with a local unitary circuit. It's equivalent to the trivial 1D phase. In these gray regions, I should say, that just corresponds to there being like the trivial phase. So these gaps here become the gray regions. These white regions are coming from the toric code blocks. On the left, you actually get a non-trivial phase, but it's unstable, even though these toric codes at any sort of instant of time here were always stable. And the reason for this is because you have a pair of M boundaries on this thin strip of toric code coming from the time when the toric code survived being rotated into space. And you have a pair of like conjugate operators here, an M operator that moves, string operator that moves an M from one boundary to the other, and a conjugate global E operator. And these map to the global symmetry and the local order parameter of a 1D Ising model. So this is equivalent to just a stack of 1D Ising models. And this is some sort of space-time picture for that, where I guess the partition function is essentially happening at some instant and being evaluated by this create and measure thing. Good. Okay, so let's get on to a non-trivial example. I think Ben explained this nicely in the previous talk, so I'm not going to go over the details of how this works. I'm just going to show some abstract picture. Good. And I'm going to use this relabeling of color code into 2 times toric code. Ask Alex about that if you want to know more. He has a nice paper on that. And there's a bunch of freedom in this, how you label all these bosons, because you can essentially swap E and M in the 2 copies of toric code. So this might not quite match what Ben wrote in his slide, but this is one choice. And it doesn't matter what choice you make, as long as you're kind of consistent. Okay, so when we turn what Ben showed us into, we abstract away the lattice details and turn it into a topological defect network in space-time. Here time's running up the page again. X and Y are along these axes. And what I have is, you can imagine I start in this in this color code, which is just 2 copies of toric code. I do some condensation, this one on the top left, which is a 1E condensation. So in this block, I've condensed 1E, and I get a single copy of toric code. I then sort of uncondense it, and this is the question Junghan was asking. So I think in Ben's kind of lattice detail story, when you measure the next round of checks after the previous one, they don't commute. So you are condensing some charge, but you're also condensing some domain wall because these things you're measuring hop charges around, but these charges don't commute with an extensive number of the previously measured checks. And so they actually have some sort of confinement. So you're not just condensing charges in that picture, you're also condensing some domain walls. And here I've kind of split this up into 2 steps. So the first step, I condense the domain walls, which is the same thing as gauging. So I kind of uncondense this E, this 1E. And then at the next step, I condense the 1M. So in the lattice model of the floquet code, this sort of period where this 2 times toric code exists is like squeezed down to nothing. Good. And if I just follow this, translating what happened on the lattice into TQFT, I have these regions where I condense 1E, I then uncondense and go back to 2 copies of toric code. I then condense 1M, uncondense, and then psi. And then it just repeats. That's the floquet cycle. Okay. How do you see that this is actually, at a high level, giving you the right properties? So let's see that we actually get this EM swap. To do this, we need to use the fact that when we kind of uncondense in each slice, we have just an E and an M, and there's some arbitrariness in how we label them. We have to identify them with something that came from a condensation. And I'm going to fix the choice here that E and this psi condensation came from the EE and the MM pair. You could make the other choice, but as long as you're consistent, you'll get the same result. This means that M had to come from the EM and ME pair. And as you go across this condensation, they're equivalent because you condense psi, which makes EE equivalent to MM under fusion with psi. Okay, so you uncondense this, you get one of these 2, but then at the next step you condense 1E. And this doesn't allow MM to pass. This doesn't commute with 1E, so it becomes confined. So if you want to just follow the paths of particles that do not pick up an extensive energy penalty with the separation, you only can follow the path of this EE, and it condenses down to a single E. You then uncondense that with respect to this sort of 1E condensation, and so it's equivalent to E1 or EE, and then you look at what can pass to the next step. Because I have 1M, I can only have the E1 possibility. I then repeat this for the 1M step, I get E1 or EM, and then finally I condense psi again, and only the EM can pass. And you see, with my original convention, that is the M particle in the psi-psi bar condensation. So over a full floquet period, you get this E to M swap. Good. The other property I think that Haah and Hastings argued for was that essentially you're just implementing the projection onto some excited space of toric code with this dynamics. So how do we see that from? So this, in a topological phase point of view, is just saying this sort of time dynamics is equivalent to like the toric code one in some sense of equivalence. I don't know how to compare things really well in space-time, so let's just rotate to space again and compare. If I rotate this to space, I just have this kind of network of defects. So now I've thrown away the time coordinate, turned it into two spatial coordinates, and this thing just sits there in space. So it's just like a regular ground state. Except it's not just toric code, it's like strips of toric code interfacing with two copies of toric code at these gap boundaries. A bit like generalizations of the ones I showed you earlier. And if you kind of just block, so these kind of things we've looked at a lot with this topological defect network framework. This would just be a kind of simple example of like once foliated topological defect network. And if you just block the whole period, you find that you get an invertible domain wall from toric code back to toric code, and we have sort of a classification of those. You see what happens across that domain wall. E just swaps to M swaps to E, so it has to be this EM swap domain wall. And so then if you further coarse grain two periods, you sort of forget about this translation symmetry, which has become a space translation symmetry here along X. If you forget about that, it's just equivalent to toric code because two of these invertible domain walls cancel out. Okay. So now I'm at the final part of the talk, which I'll go quickly over. And it's basically just to present the proposal of how I think we should describe these things at a high level to sort of classify and compare them with this space-time extension of the topological defect network framework. And then I'll just tell you briefly how you would generate examples. All right, so how do you extend the topological defect network idea to space-time? It's pretty simple. I'm just going to draw a 2+1D picture here. Now you continue to associate sort of these 2+1D liquid topological orders to the cubes of this space-time picture. On the two-dimensional, 1+1 dimensional plaquettes between the cubes, you put these defects, and they might be space-like or some space-time thing. And then where they meet, you have some 0+1 dimensional condition to satisfy to pick consistent defects there. So it's sort of the most direct generalization of these things to space-time. And the proposal, generalizing our sort of conjecture in the Spacelike case, is that these things should describe all sort of topological floquet codes. And by that I mean any sort of measurement-based dynamics where at every step you have the instantaneous stabilizer group of a topological order. So this is not proved, just a conjecture. Okay. And why is this sort of a useful way to think about things? So if you have the D+1 dimensional spacetime, we can use a lot of things we know about static Hamiltonians by Wick rotating. So as long as we don't have D+1 foliations, say we have like only D foliations, so along one direction, sort of nothing happens. We can always just rotate that one direction at a time, and now we just have a ground state problem. So we can use that to compare anything that has sort of less than maximal foliations of this defect network. This also gives you some kind of ideas about how to classify things. So if you think about these topological liquid floquet codes, which what I mean by that is that every time step you kind of have the instantaneous stabilizer group of just a topological liquid phase, not one of these more complicated ones, then you see that when you translate that into this defect network, it should correspond to just having space-like defects, which you can then rotate into just sort of some space-time defects sitting there. And you can classify that using ideas from these topological defect networks. It's sort of the simplest non-trivial type. Okay. And then finally, yeah, in the specific case of 2+1D, we can use some argument we already have, which was basically saying in 2+1D, all topological defect networks, static type, end up being equivalent to just regular topological codes after some coarse graining. And so you can kind of extend this argument to say that we expect all of these topological floquet codes in 2+1D to be equivalent after sort of an amount of coarse graining to just regular topological codes. And let me just skip over how you come up with examples. The actual details here aren't important because these examples are kind of not useful for anything so far. You take some model we already know, such as the X-cube model. We have a defect network for that in space, so static. And then we just turn this into a space-time picture. So here, the once foliated X-cube model becomes a dynamics where you just initialize 3D toric code, then get rid of it. And this one actually turns out to be stable, unlike the two-dimensional version. Okay. And the sort of mobility constraints of the fractal model end up becoming some constraints on the dynamics that your excitations don't survive in time without becoming confined. Good. And then you can play this game with more and more foliations of X-cube. So the twice foliated one, you can also reason about. It becomes quite complicated. I don't have time to explain it, but you get a bunch of 2D layers that are kind of fusing and splitting, and it does a weird sort of dynamics on a bunch of toric code layers, essentially. That sort of mixes up their excitations. And you see, again, this mobility constraint that's familiar from sort of fractons in space becoming a mobility constraint through time that you can't, certain particles can't move through time without becoming confined. You can then, go up to 3 foliations. This one gets even more complicated, but the essential features don't really change. You're just getting more confinement in space. And finally, I just want to mention this 4 foliated one. So this is beyond something you can just treat in space statically. But we have, we can just use this recipe to come up with the X-cube defect network to define this thing. And you get some funny measurement-based dynamics of the X-cube model. So I think it sort of points that with the ideas we've been using up to now, we could come up with a whole bunch of examples. And that brings me to the final slide. So I've described this kind of high-level idea that if we want to classify and abstract away lattice details of this kind of measurement-based time dynamics of topological things, we want to extend our topological defect networks into space-time. So we can come up with a bunch of examples from things we know about fractons. Are any of them actually useful for anything? And along this line, we need some kind of tools to actually convert these abstract evolutions into realizable ones with few measurements, and that we are missing. Okay, I'll leave it there. Thanks for your attention.
So if you replace your X-cube by the hard-code fracton, what would you get?
Yeah, it's kind of weird. So you can, that's like 3 foliated, right? So you can rotate 1 to time, and what you get is something that looks a bit like, these fractal spin liquid models by Benny Yoshida, where one particle can move along a dimension, but it can't move in the other 2 without making some fractal pattern. You get something like that evolving in time in a way where as you take a time step, the particle splits. So as you take a time step, the particle splits in some way. That's analogous to how it splits when you take a step along space in a fractal model, if that makes sense.
How about the E
model? Similar, but okay, so the trick is like to actually come up with really interesting examples, we need to find these 4 foliated ones. So in space, they're a fractal model, say no string model, and then we can extend them into time in some like no string way. And I have some idea about how to do that, but I don't have an example yet.
I might just be repeating a question you raised yourself at the end, but just to raise it explicitly. So it seems like you're saying these topological defect networks are both the thing that classifies fractons as in 3D and both state 2D floquet codes. So then the natural question is, can we recognize fracton-like physics in a 2D floquet code setting?
Yeah, good. That's a good question. So we have this sort of argument from the topological defect network, the static paper, that the 2D, or 2 plus 1D, so the static defect networks, although you can put some complicated stuff in there, they all end up being, if they're stable, they end up being equivalent to just a regular topological phase. So you coarse grain it all, and it all just basically goes away, and you just have toric code or something. And so what I think this means is if you look at, there's like a small hole where you're actually in this logic where you actually have like some extra defects in time, so it's a little bit different. But at every time step, you essentially should just have like a liquid topological phase. And so the guess is that nothing, once you coarse grain everything, you kind of just get a regular topological phase. So in 2 plus 1D, you're not going to get some fractonic stuff happening unless there's like a really new example that would be cool. But in 3 plus 1D, you definitely can see some fractonic stuff happening in time.
Okay, let's thank Tom again.